Welcome back. This is lecture 6 in E340 542 Networks Modeling. Today, I have really quite a bit to cover. I remember the other day, William had asked when we were going to get started actually doing something useful with all of this code. And in the middle of the cover slide, I have this picture of a very simple circuit and the output of the circuit. And that will be the first non-trivial biological motif we're going to look at. So I hope very much that we're able to get to that today. As always, I need to remind people that this lecture is live streamed and recorded. And I encourage people, if you look at those YouTube recordings, to let me know if there are any glitches or any edits that are needed. So today we are going to start out by doing a little exercise that's about how to download and interconvert between modeling formats, model specification formats. Then we will review a few of the things that we did last time. And then we will spend a little bit of time on Hill equations, and then we will start applying those Hill equations in the context of regulatory motifs. And I hope we'll be able to talk about thinking about questions to ask with these materials. Elmer pointed out that Herbert has renumbered the chapters and the appendices in the textbook. And so I need to go back and double check what the chapter numbers should be for the reading. So I appreciate being reminded of that. So one of the things that we can do with Antimony is we have very human readable code. There is a model specification standard called SBML, Systems Biology Markup Language, which is used more than Antimony. And it's, in a sense, a more powerful language than Antimony. The problem with SBML is that it's like most markup languages, you don't want to be reading it and writing it yourself. It's ugly. In particular, it uses MathML syntax for defining equations, and it's just not very pretty. There's nothing wrong with it, and you can work through it, but it's not a friendly thing to read and write. And so people generally read and write SBML through an editor, a specialized editor, a GUI of some kind. There are things like Cooperative or Cell Designer that are very good for reading and writing it. The disadvantage of that is that you need to have a specialized editor to work with it. On the other hand, Antimony has basically supports almost all SBML features, not quite, but almost all, and vice versa. And they were designed to be interconvertible. And Tellurium actually has some methods that are built into it that will convert back and forth. It also has exporters for other languages. You can export to MATLAB code. You can export, I think, to C++. You can export to Mathematica. And so what you can't always do is import, but you can export. And so I wanted to show you quickly and run a little exercise to find a model in the BioModels repository, download it. The steps will be slightly shorter if you're doing it on desktop because you don't have to get the thing onto NanoHub, but otherwise it's the same. So the first thing I would like people to do is go online and go to BioModels repository. And if you search BioModels repository, you'll find it right away. Okay, so at the top of the BioModels repository, there'll be a search bar, and it'll say individual models, and in the search bar, type EGFR. So that's a growth factor receptor, endothelial growth factor receptor. Okay, did that work for people? Yeah. Okay. All right, and you're going to get a list of models. You should get something that looks like this. So I will do EGFR. and I've got a bunch of options here. These are all published models that have the growth factor receptor in them. And there are a lot of choices, and we could pick almost any of them, but let's pick this first one here, Bianconi 2012, EGFR and IGF-1R pathway in lung cancer. Now, this doesn't display terribly well. This doesn't display terribly well in the split screen. But what you'll see here is a model identifier and then a brief paragraph summarizing what the model is about. The publication information, the abstract, how to cite it, the fact that it's written in SBML level 2 version 4, and so on. Okay. And then here at the bottom right, you'll see this little button here that says SBGN view in Newt editor. And if you click on that, it will open up the network. Okay, it should open up the network.
Yeah, it's not loading.
All right. The person who builds and maintains this website is also a friend. So if we have a problem, we can report it. It doesn't mean it'll get fixed instantaneously, but at least we can let them know and they'll try to fix it. All right, so I can't view it. Sometimes it'll view. I'm not sure why it's not viewing for me. I wonder if it's possible that there hasn't been some kind of security update in Chrome that broke their pop-up viewer.
I checked this earlier and it did launch, but it took forever. So it may just be some kind of server-side thing.
Okay, so I'll leave it running in the background and we'll see if it pops anything up after all. So the other thing that you can do is you can click on related publication here, and that will open the original paper up if you want. You don't have to do that right now unless you want to. Okay. And if we got this to pop up, which it's not today, unfortunately, we would get a hairball diagram that looks like this, which shows the network. And there's some basic tools to do layout and editing of that visualization. For very complicated networks, usually that visualization is not terribly informative. You get sort of a rat's nest of connections. But it often is helpful because instead of having to read the whole paper to see what it's about, having a single click where you can see what the network is can be quite convenient. All right. So now we're going to try to run that network. And to run that network, we're going to go up to here where it says Files and click on Files. Everybody do that. And then we will see a heading called Model Files. And if we click on Download, so you have here Download.
Model facts.
Yeah. Okay. And that should do the download. Okay. You can also hit preview. Huh. Looks like that preview button isn't working either today.
I think the server is.
Well, if their server is not working, then none of this is going to work. So we'll find out. Did the download work for people? Or did it not download? Always
This did not.
So you
Sorry. Isn't downloaded
It's not.
either.
It's not working, but there's a button you can hit. I don't know if this works, but there's another button on the like side of, and it's like a download button that just pops up and it stays on the page. But it's like a .omex file. I don't know.
All right. Well, I don't know. So maybe we will have to skip this exercise for today. It's funny because I tried this morning and it worked. Because also when I hit that download button, it takes me to a description here, whereas it should actually be giving me the code for the SBML. And I don't know quite. I don't know what's going on. They seem to be having a server issue. Let's just before we give up on this, let's go back to our list. Try one of the other ones and see if that works. If it's this file itself rather than the so I picked a different one, Kolodenko. Let's see if the visualizer works for that one. Nope. Let's try the files. Download. No, nothing I can do about that right at the moment. I apologize. So we will skip this. You can try this at home and let me know if it works. But I will just go over the syntax of what I was hoping to do with you, even if we can't run it at the moment. And I will we'll come back to that. So what we should be able to do is download that file, and we should get a file which is the BioModels unique identifier with the .xml at the end. We should be able to upload that to NanoHub. The other thing that we can do is we can open it locally in something like Notepad. One thing you have to be careful of with XML files is don't open them in Word, because Word will do things like substitute quotation marks, which will change, which will break the syntax of the file. So Notepad or something like that. And then you can use Tellurium, load SBML model, and then either the file name in single quotes, or you can actually load the model string. You can just put in a triple quotes and load the model string. And then once you've loaded that model string, you can run it using simulate, just the way we would normally. All of this syntax, by the way, is in that cheat sheet that I handed out to people. So you should be able to find it there. And then you have a single line, which is antimony model equals r.getAntimony, and that will convert the SBML to antimony. And then I can, for example, print antimony model, and now I have an antimony version of that SBML code. Now, certain things will get lost when you do this. SBML allows you to have all sorts of complicated graphical layouts. In other words, you can actually specify the diagram, the circuit diagram, and what it looks like. So most of that will be lost when you convert to antimony. So it's not a lossless conversion, but the executable code will be preserved. And as an exercise, you can go back and forth. You can convert the antimony back into SBML and so on. And so this is a pretty useful function to have. And I do apologize for it not running this afternoon online. As I say, I don't know what happened to their server today. I'm actually supposed to talk to the guy in charge on Thursday, so I will ask.
Right.
And then you can do an r.simulate and r.plot, and it'll run, and you'll get you can reproduce the basic code in the paper. So that was the exercise. I'm not going to ask you to. I mean, in principle, here I said go back to the BioModels homepage and search for a different model. In principle, if we can find an SBML model published somewhere else that we could pull in, we could do this exercise here in class. But I don't think I want to take us to do that today. But if we get this working again, I would like to run this through together and see that it works. So last time I want to remind you of a few of the things we covered. The first one was simply that we could create a list of the columns we wanted to output in our simulate function. r.simulate, after the end of start end steps, we can make a list of the variables that we want to have output. And there's a reserved word time, and then any of the variable names that we want to use. And in particular, if we have named rates, those can also be output. So that can be quite convenient. And we talked about different kinds of array manipulation, in particular, hstack, which allows us to glue arrays together columns by column. And that's useful if we want to plot lots of time series on the same graph, for example. And we use that to build a parameter scan, for example. And we also did it vertically using vstack. And there are a number of ways that we can create the initial array that we're going to use in a vstack. When we're going to do time series, we typically create an initial array, which is the time column, the list of times. For vstacks, we don't have that, and so I usually use numpy empty shape, which is not the most natural syntax in the world. But there are other ways of creating empty arrays too in numpy. There are almost limitless number of them. None of them to me are totally easy to remember or natural, but you can do. You can also create zeros and zero arrays and other things. And so then we used that syntax to plot the value of the steady state of a particular reaction versus a parameter. And so we also used the function getSteadyStateValues inside of Antimony, and had to remember this this awkward conserved moiety analysis equals true setting. You may find that sometimes that the getSteadyStateValues function fails, and in that case, the best thing you can do is simply run the simulate for a long time until things settle down. That's numerically more stable. getSteadyStateValues is much faster, but it's doing matrix inversion to get that value, and that doesn't always converge. And so this is just a reminder of the syntax that we used last time, because we're going to be using that syntax again today extensively. And so the vstack, again, the vstack basically takes a list which consists of the items that you want to stack together. So result equals npi.vstack, and then regular brackets, and then inside of the regular brackets, a list of the arrays that we want to combine in order. And we use that in particular to plot the steady state rate of production of product for an enzymatic reaction as a function of the amount of substrate. And so here we specified the enzymatic reaction at the beginning. And then we turned on conserved moiety analysis. We created an empty 2-column array. The first column will be the amount of substrate. The second column will be the steady state rate rate. Yes, Helmer.
And $sign, it's two possibilities. One, you can set it down by the variable and specified value, or you can set down in the function that is described.
Elmer notices that we are using the $sign to fix the value of S and also the value of P. And he asked the question, where does the $sign have to go? And the answer is that if you put a $sign in front of any variable, it locks its value. It doesn't matter where it is. And you only need to do it once. So the fact that I have it $sign in front of S twice is redundant. It doesn't throw an error, but if it's got a $sign once anywhere, it will lock that value. It will freeze that value.
Yeah. Because I was used to set it down in the.
Elmer says it might be more transparent if you used it where you declare the value, the initial value of S.
I think it's more informal, it's more clear. I like this more.
But Elmer is right in saying that it's a little bit awkward that it can be anywhere, so you have to look for the $sign to remember it's there. Okay. Okay. And we use this to derive the Michaelis-Menten kinetics, which we then discussed a little bit mathematically. In particular, that we got the Michaelis-Menten rate law, that the rate of production of the product is equal to the rate of reaction times the total amount of enzyme times S, the amount of substrate, divided by the so-called Michaelis constant, capital Km plus S. And if we define the maximum velocity of the reaction, then we get the Michaelis-Menten rate law, which is that the rate of production of product is Vmax times S over Km plus S. And one thing we should get used to when we look at these kinds of rate laws is ask the question, how do they behave when we have small amounts of S, and how do they behave when we have large amounts of S? If S is very small, then Km is much bigger than S. And so this is approximately Vmax over Km times S. So it's linear in S, and the slope is Vmax over Km. If S is very big, then Km plus S is approximately S. And so the S cancels out, and the rate of production is just Vmax. And Km is the half maximal value, because when S equals Km, the rate of production is Vmax over 2. So we have a rate of production which is half of the maximal value. And so there are a lot of situations in which we hear terms, parameters that are called half max. So this is one of our half max examples. Okay. But remembering that when S is large, dP by dt is Vmax. When S is small, dP by dt is Vmax over Km times S. Those are the two limits, and it's a smooth interpolation between them. And then we extended our analysis in the case where instead of binding a single substrate element, we bound multiple ones simultaneously. That replaces the mass action rate in the forward direction. Kf E times S goes to Kf E times S to the N in the rate. And we can do exactly the same analysis. And all of these examples are available in the, I didn't create a new folder there. It's still under lecture 4 demos, but they're there. And that's what I wanted you to do now. This is what we were doing just at the end of class the last time. So what I'd like people to do is to take their code, that Michaelis code that I just showed you, and change it now to replace the rate KFE times S with KFE times S to the N. And it's up to you whether you have the stoichiometry, the E plus N times S in there or not. If people and if people have lost the code from last time, it's in the student materials folder. Demos lecture 4. Typo.
I don't think you initialize ES.
Ah, yes, thank you. And yes. Still got to type. Oh, because I typed vstack wrong. I hope everybody else was able to do that faster than I was. My assumption was that you would always all load what you did last week, and I would just type it so that you could play with it for a bit. So there's the question from Pedro: is it really n molecules of S binding to a molecule of E? That's a biological question. In general, it's rare for two molecules to bind simultaneously, so it'd be more E plus S goes to ES. ES plus S goes to E2S, and so on. And so those might happen simultaneously. We're going to neglect that. Okay. Do people have this working or not? Do people need more time? See, let me know when you're ready. And I didn't put the access labels in my hand typing. Okay, so in line 3, we're saying that the enzyme binds 4 molecules of S simultaneously.
Okay. Got it.
Maybe the $sign makes it look confusing. If I take the $sign out, then it's H plus 2O.
No.
Now, in fact, if I take that 4 out, it won't make any difference at all, because the only thing that we care about is this rate here of reaction. So as long as we don't change that, we're not going to change the rate of production. But that's what I had to begin with. Pedro asks, if you see a Hill equation with exponent n, can you assume that there are n molecules of the promoter binding to the promoter? No. In general, we use Hill equations pretty blindly. And the exponent in the Hill equation is often a matter of convenience rather than derived from biological observation. And I'll come to that in just a minute. Actually, the next step of this exercise is going to be addressing exactly that question. So you're ahead of me by a step. Good question. Okay, do people have this working one way or the other at this point? Yes, no?
Yeah.
Everybody's got it?
Yeah.
Okay, so you should see something that looks like this, which is this nice curve. Okay, so now what I would like people to do is add a loop to this where you scan the value of n. Now, in principle, what we would like, I said n and there is no n. So what I would like people to do is the following. I'd like people to change that Hill exponent of 4. And this is where we have to be a little bit artificial. We're going to neglect the 4 here in the stoichiometry. So we'll get rid of that 4. We will make this exponent here of 4 and n. So then we'll have to define the value of n. And just run that and make sure that it didn't change anything, okay? Didn't change anything. And now what I'd like you to do is write a loop where you're going to scan the value of n and plot them on top of each other. And if you want to be fancy and have the colors of the lines be different or label have access have a key, that would be fine too, if you remember how to do it. Okay, is that clear what you want to do? I've suggested you could use an hstack loop like the one we used before, but you don't need to. You could just use a show equals false, show equals true in your display if you prefer. And I was saying at the beginning of class that one of the things that was frustrating was that you can't have a variable for the stoichiometry. In other words, we can't have that 4 in E plus S goes to ES be N times S. And I talked about this with Herbert, and Herbert said, well, actually, 2 years ago, we complained about this, and they added it as a feature to Tellurium. So you can actually have a variable stoichiometry. But the version of Tellurium that's up on NanoHub doesn't support it. It's an older release, so it doesn't have it. So when we get the NanoHub version of Tellurium updated, then we'll be able to have variable stoichiometry in the NanoHub. So I'm going to write some code to do this, but please do it on your own. Don't wait for me to don't follow me. I'm not going to do it in a nice way. I'm going to do it. I'll do it in a dumb way. Oops. Ah. I mean, the way I did it, I didn't use the vstack, the hstack. I just did put everything inside of a loop where I changed the value of n. I decided not to try to use the list form. I did a plot array with show equals false. And then I did a plot with show equals true at the end to display the plot. And I was trying to add a key, and I'm not exactly sure why the key is truncating my number of decimal points so that it's not displaying 10, 12, and so on. If I go from 0 to 10, step of 1, it's all right. That works. I'd have to do something where I fix the number of decimal points. I think that's the problem is that. Anyway, I'm not gonna mess with it right now. Elmer is trying to debug it for me. Did anybody else solve it in a different way? I'll put this in the chat. It's not the most elegant solution, but it does the basic job. Did people get something like that? It's also true that, by the way, that the Hill exponent doesn't have to be an integer. Okay, so the question was, what did you find? And I hope that people got something that looks somewhat like this. You'll see that this first blue line, the first blue line here is the Michaelis-Menten line. And then as we have the N go up, and let me cut this back. I had added some lines here. Let me make this just fewer of them so it's easier to see. As N goes up, we see something that gets more and more sigmoidal. If we keep going to very large N, we'd get something that looks like a step function. We'll notice that the value is always 1/2 when S is equal to 1. And that's because we set our K, our capital K, our Michaelis K, to be 1. And so let's think about this. The rate of production is R times E total times S to the N over K to the N plus S to the N, where K to the N is given by K reverse plus R divided by KF. Let's look at what that is. K reverse is 1, R is 1, K to the F, KF is 1, so this should be 2. So K should be 2. So that actually seems to disagree with what I have here, doesn't it? So it looks like the critical value here is 1. No, actually that's not true. K here's 2, and K equals 1 is our half maximal value. Let's see. Did I do something wrong? The maximum velocity of reaction should be R times E total. E is 1, R is 1, so the maximum velocity is 1, and the maximum is 1. So that's right. And I have a different version of this here, defined in a function which I called plot hill, which is plotting essentially the same thing that we've got here on the screen, although with a lot more elegant code. And again, the median value of K, that half maximal value, and here I've defined K to be 1/2, and this is known as the Hill function. And the Hill function has 2 parameters. it has the value of K, the value at which the rate is half of its maximal value. The concentration at which K is at the rate is half of its maximal value. And it has the exponent n, which defines the slope in the middle. If n is bigger than half, I'm sorry, if the exponent n is bigger than 1, then the value at 0 is 0. The slope of the line at 0 is 0. The slope is maximal where s is equal to k. And the value for s being very large is 1. And the slope when s is very large is 0. If n is less than or equal to 1, I'm in the Michaelis regime. In this case, the slope is maximal at 0. The slope is intermediate at 1 at k. And again, as s gets very large, the slope goes to 0 again. And I could change my function here. The labels aren't going to work for it, but I could change my function here to plot what happens, for example, if the exponent were between 0 and 1. And this is going to give me a different kind of set of curves that are what happens if you actually go below the Michaelis threshold. Having a bigger than 1 is called cooperativity. Having an n less than 1, I don't think has a name. It's hard to imagine how you'd have the enzyme react with half a molecule of the target, but as a mathematical abstraction, it's okay. Let me put n back bigger than 1. It's a bit confusing to see. So the larger n is, the more step-like our response is. This is called a sigmoid. And there was a question or a comment some time ago about the shape of the sigmoid. And using these power laws, x to the n over k to the n plus x to the n gives us a sigmoid with a particular shape. And there are alternative sigmoids that one can use. In particular, the hyperbolic tangent has the same kind of sigmoidal behavior. And the symmetry of that is a little bit different. You'll notice that if I look at my sigmoid here, it's precisely 0 at 0. But to get it to come to a value of 1, I have to go to s equals infinity. So it's not completely symmetric. If I exchange x, if I take xs and replace it with 2 minus s, I don't swap the shape. If I use the hyperbolic tangent, it's symmetrical in the x-axis. And that has some advantages. But the Hill function is the one that we typically use in reaction kinetics. If we make our n very large, suppose we make n 10 to 100, we'll see we get really step functions. Okay. Now, coming back to the question that Pedro asked earlier, which is how do we know what N should be? Well, in some cases, we really do know that 4 molecules of A combined with 1 molecule of B. And in that case, we expect a value of N to be 4. More generally, we will actually use the Hill exponent of N as a fitting parameter. We will say, we know that there is a sigmoidal response. We don't know exactly how sharp that sigmoidal response is, and we will try different values of N to see what works. In most practical simulations, we assume to start with that N is 4. That gives an N of 4 gives us something that is clearly not clearly sigmoidal, but is not super steep. And let's just look around 4 through 4 to. In general, we will just start with N equals 4 when we're using the Hill equation. Now, again, if we know something about cooperativity, then we can sometimes calculate what it should be. Usually, we find that mathematically the value of N that we need to use is larger than what we could justify on biological grounds. And that there's a whole set of interesting literature about why that might be the case. Okay. One of the things that's very convenient about the Hill function is that it is an increasing function of the concentration of the x-axis. It has a partner, which is called the decreasing Hill function. And it also has a half maximal value at s equals k. However, it is equal to 1 at 0 and goes to 0 at infinity. It also has a maximum slope at s equals k. In this case, a maximal decreasing slope. And it also has a partner, the decreasing Michaelis function, which is what you get when n equals 1. And there's a nice symmetry here. All we need to do to get the decreasing value is replace the value s in our numerator with k. So x over 1/2 to the x to the n over 1/2 plus x to the n is replaced by 1/2 to the n over 1/2 to the n plus x to the n. And that's a decreasing Hill rate law. And so if we want to know what happens if something is a decreasing function of s, and we now want to ask the question, what would happen if it were a decreasing function of s? We just change that one symbol from s in the numerator to k in the numerator. And it has the same kind of basic properties. Again, it's 1 when s is 0. It goes to 0 when s gets large. It's 1/2 when s equals k. And for n greater than 1, it has maximal slope at s equals k. It has slope of 0 at 0. And we can put these next to each other. Let's before we do that, actually compare the time series for the. We assumed here that we were looking at a steady state result. Let us actually look at the time series for the enzymatic reaction, which is what we have written here, and compare it to what would happen if we assumed that everything happened at once in one go. So to the Hill approximation. The steady states with the dollar signs are going to be the same, but let's actually look at the time series. So is it clear what you need to do here? We have typed already, modulo some dollar signs, the enzymatic reaction, which is the top one. I want you to add a second reaction, And you'll need to give these variables, the species a new name like E1 and S1 and P1, because you want this to be a separate reaction. And I want you to plot these two things on the same plot and see how similar or different they are. Is that clear? William, does that make sense? Yes, no?
Well, I just don't understand. Would you write it within the same block?
Yeah, you can do that. So what we'll do is this, we'll get rid of our
Okay.
dollar signs here.
Okay, okay.
And now I can create a new, I'll do it with you. J4 is going to be, we'll say E1, because it has to be, we have to be separate. We could have two separate, we could create two separate strings, model strings, one for one and one for the other. Or we can put them into the same thing. It's up to us. Probably you're right that it would be more correct to have them as two separate models. But I'm going to leave them inside for the moment. I'll put my 4 back here for the moment.
Wait, sorry, I'm getting confused. You're writing E total equals E plus ES, but what about the E1? Does that not matter anymore?
Okay, so you're right that I should probably have set E1 equal to 1.0. So as I say, my instructions were to try to do it on your own and not watch what I was doing. But
No, well, yeah, but I was just confused. Because I
Well,
don't understand.
I wasn't actually planning on doing this exercise. I was planning on just waiting for you to do it, and so I was doing it off the top of my head here. So let me,
Okay.
if I'm going to do it, let me walk you through what I was thinking of, because just typing and not saying anything is not very useful. So I decided, okay, I'm first going to start with my existing code, and I put the 4s back in, just to put it back the way it was. And then I'm going to write a new reaction, which is going to be this one here. E plus 4s goes to E plus P at a rate V max S to the N over Kn plus S to the N. I'm going to do a new reaction like that. And because I'm putting it inside of the same string, I, as you point out, have to give all of my variables new names. So it can't be E because I don't want it to interfere with my old one. So I called it E1, S1, and P1. And now I need, this should be S1, and this should be S1. And the rate here I defined V max was R times E total. And I have to define what K is. And here it says that K should be 1/2. Actually, here it says K should be 2, which seems to me to be wrong, but we can try that. we'll set k equal 2 and it'll give us the wrong answer. So there's a typo here somewhere.
Should R be a different variable also?
Well, r is a parameter, so r is not changed. But if you want, I can make r something different. I can make r, give r its own value for the second. That's a reasonable suggestion. Okay. And I need to give my value of k. And this says that k should be, capital K should be 2, which I don't think is right, but let's try what happens. Okay, it's 2.
Well, there's no E total is E plus ES, like ES, right? But there's no ES in the equation at all.
That's right. There is no ES in this equation. Because I'm not doing the intermediate step. I think my typing this has confused people. In other words, I think if you were asked to just type this formula, you would be able to do it more easily than it is trying to watch what I'm typing. So why don't I hide what I was doing and have people simply type this reaction? Okay. E plus n goes, E plus s to the n times s goes to V max s to the n over kn plus Sn goes to E plus P. Okay, just that. And I think if you do that, it'll be clearer for people than if you try to follow along with me. So I think what's happened is that I've distracted people from what the core idea is here. That's a mess. And I actually gave more detailed instructions. Plot the amount of ESN and P for the enzymatic reaction by itself, and then just plot the production rates. So let me do that. So that's my initial one. And I did something wrong here because I've got something contaminated here. Let's see what I did wrong. ES goes to 4E. ES, let's see. KF times ES. ES goes to E4 plus 4S. ES goes to E plus P, that's right. E1 plus 4. Okay, why am I getting a jump in ES? So ES is changing discontinuously in, oh, because I've got S is 10. Set to have S equals 1. There we go. There. So this is the enzymatic reaction by itself. And now let me plot the other one. And make sure that that's working all right. I didn't set S1, so I need to set S1. And E1, I set there, okay. And so let's look at the second one, which would be just would be J4 and P1. So it looks like that. So now let me do what what's asked here. Let me look at the rate of production of P for both reactions. So the rate of production of P for both reactions would be plotting J3 and J4. So let's plot J3 and J4. And we get that. So I would like people to try to do this. This is actually not, I made it more complicated than it needs to be. In particular, I've got some scaling things that are wrong here, which isn't helpful. I should have K2 plus R divided by K1 in the denominator. So let's see, let me put this in the way it's actually supposed to be written here. K2 plus R divided by K1. And then I called that SA instead of S1, but otherwise that's correct. And the values are all 1, which is correct. So that should be right. Because I didn't define K2. K2 should be, sorry, K2 is the I called it K forward and K reverse is K, should be K2. The point of this exercise, and that maybe it's worth coming back to the point of this exercise, was that the Hill approximation is an approximation that neglects, remember that we said before that it takes time for the complex to form. In reality, it takes time for E plus NS to make ESN. Once we've made ESN, the output, the production of P is the same. And so what we see if we compare our two results is the rate of production of J for our second one starts out very large and then decreases as we run out of substrate. The rate of production for enzymatic reaction starts out at 0 because we have no complex. It takes a while for the complex to form, and then it gradually decreases. If we look at long times, they're almost the same. And so they're not exactly the same. The time course of these two things is not exactly the same. So this approximation is an approximation. It's not reality for this reaction. Let me give you, in case you're still working on this, and it's not very pretty, let me give you the code in the chat. It's all online as well. Phil and enzyme time series.py. It's all there. Okay. And now you can say, now why is there this what is going on here? One of the differences is we can't ask what the long time rate of production of P is because we run out of substrate. In long time, we have no substrate left. And so it only makes sense to ask this question if we fix the amount of substrate. So the next thing that we need to do is to $sign the amount of substrate and run it again. And we have to do that twice because we have to $sign both the amount of substrate for the two different reactions. So try that. What happens when you do that? Somebody? Did anybody get that to work? Did things look more similar, more different? What happened? You can start with the code that I put in the chat, or if you had your own code, that's fine.
It just looks like the rate of J4 stays constant.
Okay, so what do we get? So in the second one, the Hill equation, the rate of production is now constant. Why is that? Well, what is the rate? The rate is V max S to the N over K to the N plus S to the N. It depends only on S. And so if the amount of S is fixed, that's a constant. It's always the same. In the first one, it takes time for E plus Sn to make ESN. Once it's made it, the rate of production of P is constant. And so what we see at the blue is the time it's taking to make that complex. It's the time it's taking for the enzyme to bind 4 molecules of S. And so what we're seeing is that initial equilibration between E plus SNS and ESN. That's what this blue curve is here. Were people able to get that to run? or not? You got it. Interesting. So all we had to do was add $2 to our code, one here and one here. All right. Now I asked you, and I don't think since we're a little bit behind here, I'm not going to have you do it. You can rerun the conserved moiety analysis and everything else that we ran here before for the two and compare the results. And what you would find is that the long time behavior is identical. And so in this case, we've got a very strong statement, which is that the time dependence of these systems is different. The time dependence of the enzymatic reaction and the Hill function is different. But at steady state, if the amount of substrate is constant, the two are identical. And so if we only care about long time behavior, we can make the substitution of the Hill function. We don't lose anything. If we have a time varying substrate concentration, then over the time it takes for the enzyme to re-equilibrate, we'll get the wrong answer. And so if the rate of variation of the substrate is fast compared to the equilibration time, we're going to get the wrong answer when we use the Hill function. If the rate of change of the substrate is slow, then we can get away with it.
So we have to think about what our model, what we want to stimulate when not is right. So
Elmer asks, that means that we have to think carefully about what we're going to simulate before we decide whether we need to write the enzymatic reaction out or whether we can get away with the Hill function. And absolutely, Elmer is 100% right. People often will use the Hill function without thinking about whether that approximation is legitimate or not. We do this quite a bit in these kinds of models.
this is mainly done because of setting process speed or just easier to write. I mean,
Elmer says, why would you make this approximation? Well, in the case of writing an enzymatic reaction of our enzyme reacts with 4 molecules of S, we know what the chemical reaction is, we know what the mass action rate law is, and we can write it down. In general, when we're talking about gene regulatory networks or signaling networks, we don't really know what the details of the chemical reaction are. And so we don't actually have the equivalent of the enzymatic reaction available to us to write down. We only are trying to do something phenomenological. We know that when we increase this, we get an increase of that. But we don't know the detailed functional form and how it got there. And so the answer is that in general, when we use Hill functions, we are encapsulating our ignorance about the system in a controlled way. And what I'm telling you here is not that you shouldn't do that. It's not a bad way to approximate things, but you should be aware that potentially the temporal behavior of the system will be wrong, at least over short times. And so that's something that one probably won't appreciate until later if we get to it in the class. But it's something that I want to bring up now because it's if you were doing this in a chemistry class, you would spend a lot more time trying to understand this.
and it's always the cooperative enzyme function that we replace. It's not, I mean, if there will be inhibition or so, it will be cut later on, right?
I'm sorry, I didn't hear.
So it's always a cooperative enzyme function that we replace. I mean, when
So-
you have dynamics like inhibition or so, then we shouldn't use any function at all.
So Elmer says, when do you use the Hill function? Is it only when you have an enzymatic reaction, or is it in other situations as well? In particular, why would you ever have an inhibitory Hill function? And so there is, in fact, a bit of a non sequitur or a logical disconnect in the way we typically work with these systems. And that is the following. We typically say, here is a chemical reaction. It's a cooperative enzymatic reaction. And this cooperative reaction happens to have the equilibrium rate of production of product, which obeys the Hill equation. Now that we've written the Hill equation, we're going to use it in situations which have nothing to do with that. So we've shown that there is a situation in which the Hill equation is correct, but we have not established when it is appropriate to use it. So in a sense, you're right. I could have just written a priori, we have a situation in which we have a low value under certain circumstances and a high value under others. We want to interpolate between the two smoothly, and the Hill function is one way of doing that. And so that was actually what I wanted to come to next. I'm going to skip this. This is just showing that the equilibration between the two systems is exponential. And so that the enzymatic reaction approaches the Hill, the steady state Hill reaction exponentially fast. And the equilibration time actually depends specifically on the forward and the backward rates. But I don't think I want to do that today. I'm going to introduce the Hill function in the context of solving a problem, which is going to be one of a homework problem that we're going to assign. And so the homework problem will look like this, and we're going to solve problem B, subproblem B in the homework. So what I would like to do now is come back to the problem of motifs. And this comes back to what William asked the other day, which is, how does all of the things that we've been doing relate to the biological problems we want to solve? And so we've spent a considerable amount of time. We've spent 5.5 lectures developing mathematical formalism, talking about how to write models, how to solve models using antimony, how to plot things, and so on. But we haven't actually looked at any significant biological problems. We've looked at one chemical reaction, which is the enzymatic reaction. And so Herbert actually in chapter 1 of his textbook has a series of motifs. These are gene regulatory motifs, as it happens, which are common circuits that you find in biological systems. In reality, of course, they're more complicated than that, but these are the cores of these systems. And he asks you to think about these circuits and asks you to describe what they do. And based on this, I created a homework problem, which asks you to actually not only think about what they do, but write a small simulation to analyze what they do. And some of these circuits have 2 chemical species in them, and some of them have 1. And so the problem is written as if there were always 2. But for the first ones, A and B, we only will ask for 1. And the first thing that you want to do is you want to write a simulation that simulates the operation of the circuit in time and figure out about how long it takes to do whatever it does to equilibrate. And then you want to write a simulation where you change the initial values of A, if there's 1 value, and B, A and B if there are 2, and ask the question, do they reach a steady state? And if so, is the steady state independent of the initial values or not? And in particular, if you got those Michaelis or Hill constants K, what happens when you're bigger or less than K? Because typically that's the threshold for things happening. And then the question will be to change key parameters in the simulation and ask whether those long-time behaviors, those steady state behaviors, change as you change the parameters. And then something that we're not going to do right at the moment, but that we could do in principle, would be to ask if we perturb the system, if we kick the system in some way, how does the system respond to temporal perturbations? And so we're going to be focusing on autocatalysis. The production of A promotes the production of A. And actually here, I'm not following my own notation because I have a pointed arrow instead of a blunt lollipop arrow, but that's what Herbert uses. And we're going to start by looking just at the diagram. And I'm going to walk you through the steps to take this diagram into something that you can simulate and ask questions about. And you might say, well, looking just at this diagram, I have very, very little information. How can I actually come up with something meaningful just looking at this little arrow diagram? But in fact, if you're systematic and think about this in an organized way, you can in fact build up step by step to something that you can understand. And that's really, if I was pushing a little bit in terms of trying to get through the earlier part of this class, it was because this is really where I think we begin to do something meaningful biologically. And so I didn't want to spend too much time, important as it is to get the code working, I didn't want to spend too much time on that because I wanted to focus on the thing that I thought would be more interesting to people. So the first thing that we had talked about, and we'd gone over this briefly before, and I'm going to show the signaling network one quickly, and then we're going to come back and do the gene regulatory network one in a little bit more detail, is how we interpret arrow diagrams. And so if we have a signaling network, and we've seen this slide before, and we say that A promotes S2, what that means is that there is something that is producing S2, and the rate of production of S2 is regulated by A, and A is an activator, which means that the more A we have, the more S2 we get. And when we see that, our default assumption is going to be that the rate of production of S2 will be a Hill function of the amount of activator. And you could say, why is that? Well, there are a couple of things we know. If we have an infinite amount of A, we still can't have an infinite production of S2. So it has to saturate. If we have no A, we probably don't want to be producing much S2. So the amount of S2 being produced should be an increasing function of A. Now, the shape of that function is not so obvious, but there has to be some value of A at which the production is half of its maximal rate, and we'll call that capital K. Okay. Now, if we saw something that looked like the second one, which is S1 goes to S2 at a rate that's modulated by A, now we have something a little bit different because now we actually know what our source is. And so now the rate of production of S2 is going to depend on two things. It's going to depend on the amount of S1 that we have, and it's going to depend on the amount of A that we have. If we assume that we have mass action, then the rate of production of S2 is proportional to the amount of S1. Pretty often, we will assume that there is a Michaelis dependence of the rate of production of S2 on S1, in which case our net rate of production will be our Hill function, A to the n over K to the n plus A to the n, for the regulation, times V max times S1 over Km plus S1. So we have a product, one of a Hill function and one of a Michaelis function. If we're going to have a lot of reactions that are going to interact with each other, the product of reaction 1 affects reaction 2, the product of reaction 2 affects reaction 3, the product of reaction 3 affects reaction 4. We want to be able to wire things together. Then we need all of our ranges of our S's to be and A's to be compatible with each other. Just the way if we're doing digital electronics, the voltage that defines a 1 or a 0 has to be standardized if we're going to be able to interconnect things. And the way we can do that in our circuits is by setting those Michaelis K's to always be the same value. You could set them always to 10, and then everything will scale between 0 and 20. In my case, I like to use a K of 1/2 so that the values of S go between 0 and 1. Now, in these circuits, it's allowed, S can't go negative. Concentrations can't go negative. Concentrations can go above 1, but they're never going to go much above 1 in these circuits. And so if you set all of your Michaelis K's to be 1, excuse me, to 1/2 to begin with, then you can wire your circuits together. Now we'll discover later that we're going to have to make some adjustments to that. But to begin with, that's a reasonable approximation. Yes.
I see that you can use the Hill function, but what I don't see is, I mean, when you have now A and you produce A, this case that was no, then you had up something exponential, and why should it flatten up again? Why can we approximate it with the Hill function? Why would it not just grow exponentially?
So Elmer says, why would we assume that the... I'm not sure what I understood what you asked.
Because somehow we have now a step function that's what we are assuming, or approximate when you have a Hill function, right? But when we just look at the diagram, we would just always produce more S2, so it would grow exponentially till...
So Elmer is coming back to this and saying, why should the amount of... So Elmer is asking the question, why should the amount of S2 saturate?
Yes, yeah.
And the answer is the amount of S2 doesn't saturate. We're talking about the rate of production of S2.
Yes, yeah, great. Yeah.
And so the rate of production of S2 can't be infinite. We can't produce S2 infinitely fast. However, if we don't get rid of S2 somehow by having it decay or use it in some other reaction, we'll wind up with an infinite amount of S2.
Thank you. Yeah.
So Elmer's question was a reasonable. It was good insight. Okay. Similarly, if we have inhibition, if we see R inhibits S, then we have S being produced out of nothing. And the rate of production is a decreasing function of the concentration of R. And we'll use an inhibitory Hill function, V max times K to the N over K to the N plus R to the N. This is where having the K and the N be symmetrical is very useful, because we just have to change that one symbol in the numerator to switch from activation to inhibition. Similarly, if we had S1 going to S2, we have to multiply that rate either by S1 or by a Michaelis function of S1. As before, if we match the Ks, we can interconnect these things, and they'll be compatible with each other. If we're doing gene regulatory networks, the initial diagram may look slightly different, but the way we interpret things is similar. Here we have protein 1 activates the production of protein 2. And this is what we're going to be simulating, except that it's going to be protein 1 activates the production of protein 1. We interpret this as protein 1 binds to a promoter site turns on the gene that produces the messenger RNA for P2, and that produces P2. Again, we're going to interpret this complicated set of steps in terms of RNA synthesis and protein synthesis, simply as there is some production of protein, P2, and the rate of that production is controlled by P1. As we mentioned before, and as Elmer very pointedly pointed out, if we're producing P2 and we're not getting rid of it, the amount of P2 will go to infinity. And so whenever we see a diagram like this, even though it's never written, there is an assumption that P2 decays. And so when we see P1 promotes P2, and we want to interpret that as chemical reactions, we interpret that as nothing goes to P2, and P2 decays to nothing again. The rate of production of P2 is controlled by P1, and we have to write the rate law for the second term as well. In general, now we have to decide what those rate laws are. And we are going to assume for gene regulatory networks that the rate law of production of the protein is a Hill function, V max times P1 to the N over K1 to the N plus P1 to the N. There's an additional twist that we apply to gene regulatory networks that we don't usually apply to signaling networks. And that is that gene regulatory networks are leaky. Even in the absence of the promoter, P1, we often will have a small rate of production of the gene product. And that's called basal rate of production, and we'll give that the letter lowercase b. Now, very often we'll set b to 0, but there are going to be systems where we need to make b non-zero. Okay? So the velocity of production of P1 will be a basal rate B1 plus V max times P1 to the N over K1 to the N plus P1 to the N. Our decay will always assume first order decay. The rate of decay is some constant, K decay, times the concentration of P. In particular, at steady state, that means that the amount we're going to get will be that V1 of P1 divided by KD2. If we can rearrange our terms a little bit to combine things, and I'm not going to insist on this now. I will refer people back to this slide if they want to go into it. But the decay time of the chemical sets a time scale for the chemical reaction. And it's convenient to absorb that decay time for the chemical into the rest of the equation. Makes life a little bit easier for you. But we don't have to worry about that right at the moment. The main reason that we want to do that is that we would like the equilibrium concentration of our chemical not to change when we change that decay rate. And that's why we make this approximation. Again, I'm not going to, since we're a little bit behind, I'm not going to go into the math on this one right now. You'll have the slide there if you want to look at it. You're not going to need it for our exercise. Okay, for our inhibitory reaction, it looks exactly the same. Here, P1 is inhibiting P2. This is translated into nothing goes to P2. P2 decays to nothing. And in this case, we have a decreasing Hill function. In this case, B1 represents the rate of production of the gene, even if there's a lot of inhibitor, because our inhibitor is never completely successful at turning the gene off. And as before, we have first order decay. The rate of decay is linear in the amount of chemical. And so again, we can write the ODE for the amount of P2. It's C1 times KD2, which is just a constant, plus our Hill function as P1 minus KD2 P2. Sorry, I'm going to skip the details here, but we can compare these two. The inhibitory function, the activator has the form, the time derivative of P2 is a constant Basel rate of production plus a Hill function of P1 minus a decay rate times P2. The equilibrium value, the steady state value of P2, is that constant C1 plus K1 times P1 to the n over K1 to the n plus P1 to the n. So we get a sigmoid. Here I've used a Hill exponent of 8. The inhibitory one looks exactly the same, except it goes down instead of up. And its half maximum value is always at when the concentration of P1 is equal to K. Sometimes it's useful to think of these as switches, where if P1 for activator, if P1 is less than K1, we don't produce any product. And if P1 is bigger than K1, we produce product. For the inhibitor, if P1 is less than K1, we produce product. If P1 is greater than K1, we don't. Again, the key thing to remember is we see P1 going to P2, promoting P2. We write the rate B1 plus Vmax P1 to the n over K to the n plus P1 to the n. We see P2 inhibiting P3. We write the rate of production of P3 as B1 plus Vmax K to the n over K to the n plus P2 to the n. The value of K is critical because it sets the threshold of P at which we go from low rate of production to high rate of production. Genes typically turn on and off pretty sharply as a function of the concentration of the activator and the inhibitor. And so we typically use an exponent of 4, which is a relatively soft dependence, or 8, which is more switch-like. So now, what I'd like us to do together in our last time for today is I want to write this, to use these ideas to solve this problem. Here, I haven't written the letter A. I've got a circle standing in for A. You could call it X or B if you want instead of A. But I've got a statement that a chemical promotes its own production. So I have drawn the figure for P1 promotes P2. In this case, it's A promoting A, and I've reminded you how to interpret it. And so the first thing I'd like you to do is write a rate law for this diagram and convert it to a rate equation. Based on what we just went over, I'd like everybody to take about 2 minutes or 3 minutes and write down what is, call it A instead of, or P1 if you like. Let's call our chemical A. What is the concentration of A versus time for this diagram? What's the first thing that I have to do here? If I want to give this a rate, if I want to write a rate law, I have to give my species a name. And I've said to call it A. And I have A promotes A. So what does that mean here? A activates A. And so that means the rate would be what? B1 plus V max times A to the N over K to the N plus A to the N. That's it. That's all you have to do. So that's the rate law. Now, what's the second thing you have to do? The second thing to remember is that we said before that whenever you have a reaction like this, you also have to have the decay of the chemical that you produce. And so you have to have A go to nothing at a rate K, lowercase k times A. That's it. That's all you have. And so the chemical reaction is this. Nothing produces A at a rate B plus K1 A to the H over, here I scaled it by 10 instead of a half. I said to use a half, but Herbert likes 10. So I'm using Herbert's value of 10. And then A decays to nothing at a rate K2 times A. We have we have a rule. We have a rule that if P1 activates P2, we read that as nothing goes to P2 at a rate B plus V max P1 to the N over Kn plus P1 to the N. In this case, we have A activates A. So we have nothing goes to A with the arrow, and P1 is replaced with A in the rate. That's it. And then we remember that we had a rule that when we have nothing, when we have production of P2, as Elmer pointed out, we can't have an infinite amount. So P2 has to decay. And so that means A has to go back to nothing. And if we have no information, we use mass action. So the rate of decay is linear in A. And so that's how we get that equation. So now I'd like people to write that reaction, that chemical reaction, and simulate that time series for that. Okay, so now take that reaction law, that chemical reaction, and write it in antimony and simulate it. And Herbert gives us particular values that he wants us to use for B, K1, K2, and H. So why don't people write that and see what they can get, and try it for different initial values of A. In particular, try it for A less than K and A bigger than K. Okay, if you've got that working, write a little parameter scan where you change the initial value of A and plot the values on top of each other. This is not a hard thing to write, I hope, at this point. Nothing goes to A at a rate B plus K1 times A to the H over K10 to the H plus A to the H. A goes to nothing at a rate K2 times A. I said K1 is equal to 2, K2 is equal to 0.1, B is 0.2. I started with an initial value of 1, and H is 4. I ran it for 100 time steps, and I probably should use the plot array function rather than the plot, because I'm going to want to overlay things. No labels here. I get something that looks like that. If I start with A equals 1, it goes up and it saturates at 2. If I start at A equals 10, it goes up to 20. And now I'd like you to write this where you change the initial value of A and run it for lots of different values of A. Oops. People able to get something that looked like that? So this is our first interesting result, perhaps. Well, in some ways, the fact that we get the Hill function and the Michaelis function was interesting. But this is our first biologically interesting result. Here we have the simplest possible circuit. A promotes the production of A. And what this tells us is that if the initial value of A is low, the value of A stays low. If the initial value of A is high, the value of A goes to a high value and stays there. And so what this is called a bistable circuit. The final outcome depends on the initial value. So now what I would like you to do is calculate the steady state value of A and plot it as a function of the initial value of A. And in this case, I would probably suggest that you don't use getSteadyStateValues, although you could try. Well, you could try getSteadyStateValues. So I want you to plot on the x-axis is the initial value of A, and in the y-axis, the steady state value of A. And you probably want to use the code that we wrote earlier, not the code that I just showed here. Okay. In this case, I would have done better to save my old code instead of overwriting it. And again, I'm going to do this, but please do it on your own. Try not to use what I wrote. Boy, that didn't do what I expected. So get steady state values didn't work for me. But running it over the time did. Did people get something? What do you need to do here? You need to, you've written this, you've got the code that runs the simulation. Now what do you want to do? You want to create an empty array where you're going to keep track of the initial value of A and the final value of A. You're going to iterate over the initial value of A. And if we look at here, the range of initial values of A was between 0 and 40. So I'm going to iterate for initial values of A over the range of 0 to 40. I'll reset my simulation. I'll set my initial value of A. I'll run the simulation for a while. I'll stack the initial value, comma, the final value, and then I'll plot it. And what I see is that if A is less than about 7.5, I get a final value of about 2. And if A is bigger than that, I get a final value of about 22. So let me give people the code. I want everybody to be able to run this code. We're going to run out of time, but I want to make sure everybody can run this code. So you'll notice there are only 2 output values. There's an output value of about 2.25 and an output value of about 22. That's it. So now I want you to do one more step. And you can use the code that I put in the chat before where we scan 2 parameters. I now want you to scan the value of each of the parameters in the simulation separately. And instead of stacking A initial and A final, I want you to stack the parameter value and the value of A final. So for example, if I'm changing the value of B, the initial value of B that I was using was what? Let's see. The initial value of B that we had here was 0.2. So change values of B from 0 to 1. For each value of B, run over the different values of A, find out what the final value of A is, and stack it. Does that make sense? And you don't have to do it. You don't have to do it for all possible values of A. All you really need is a low value and a high value of A. So you could do it for 2 values of A. So think about how you might do that. Okay. So you want to plot on the x-axis, you're going to be plotting the value of B. Once you've done it for B, you can do it for K1 or K2. The y-axis, it will be values of A. And in some places, there might be 1 value of A. Some places there are 2, 3, 4, multiple possible ones. So you have to think a teeny bit about how you might write the code to do that. It's basically the code I had written and put in the chat a few minutes ago. A simple modification of that. This is called bifurcation analysis. And this is the main thing that we do in analyzing networks. To begin with, if you're worried about doing it for large and small values of A simultaneously, why not just change the code that I gave you and just scan the value of B and keep the initial value of A constant, keep the initial value of A 0 and see what happens, okay? In that case, you only have to change 2 symbols in the code that I gave you. Okay. Now, I may have made a mistake myself. I'm not sure. So that was for a small initial value of A. And now I'm going to do it for a large initial value of A. So I know what happened. I started with my initial value of A here was 10. Good. Here, we'll leave it this way. I'm going to set my initial value of A here to be 0. So that was for small initial value of A. Now I'm going to run the same thing again for large initial value of A. I'm going to do this in a non-elegant, non-Pythonic way. Elmer can come up with a much more elegant way of doing the same thing. So let me walk you through what I did, but I really would like it if people could try to do these things on their own gradually. So what did we do? We took the code that we had that scanned the initial value of A. And I said, instead of scanning the initial value of A, I'm going to scan the initial value of B. I'm going to scan the value of the B parameter B. And I know that B was set to be 0.2 initially. So I know it's going to be in a range between 0 and 1. So I set B in a range between 0 and 1 steps of 100th. I reset my simulation. I set the value of B. I have to overwrite the value of A. I'm going to start with a small value of A because I expect there to be 2 outcomes. I simulate for a long time. I stack the value of B, comma, the final value of A, and I put it into a plot, but I don't show the plot. I now do exactly the same thing again, except that I start with a big value of A, here 40, I stack it up, I add it to my plot, and I show the plot. And I get this. Does anybody want to explain to me what that is showing? What is the y-axis? William? Can you have an idea? What is the y-axis here? The y-axis is what?
I was thinking out loud. Isn't it the steady state of A?
Perfect.
Yeah.
Okay.
And then the bottom is just the amount of, or whatever B is.
Right. B is a parameter. It's the basal rate of production. And so what this is saying is if the basal rate of production, the lower curve here, and maybe I should have had a different color for this, the lower curve is what happens if my initial amount of A is very small. The upper curve is what happens if my initial amount of A is large. And I can check that because I could not do this second plot. Well, I can't do that. I'll not do the first plot. The first plot is when the initial amount of A is small. And I get that. So what happens is the following. If B is less than about 0.4, if the initial amount of A is small, the final amount of A is small. If the initial amount of A is large, the final amount of A is large. If B is bigger than about 0.4, no matter what my initial value of A is, I always wind up with a lot of A. So as I change the value of B, I go from a situation where B is small, my final state depends on my initial state. If B is big, I always get a lot of A, whatever my initial amount of A was.
Copy is usually given by biology, right?
Well, there could be something that regulates that. There could be B could be something related, say, to a toxin in my environment. B could be a growth factor. B could be a lot of things. But the key thing is that as I change the value of B, I go from one steady state at high values to two steady states at low values.
You said B is the base value, which you said is kind of leaking of the network before.
That's right. So why don't you now change, do you think the last thing, we've got 2 minutes left, could you change this to not scan B, but why not scan K2? Change the value of K2 and see what happens. How do you do that? Well, every place there's a B here, make it a K2. Why don't you do that with me? See what happens. K2. 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 Oops. K2. K2. Again, if I were more Pythonic, it wouldn't be quite so annoying to have to change the values in so many places, but that's life. Doesn't take very long. K2, 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 K2. What happened? Does anybody have a result when you scan K2?
But K2 is what is
K2 is the decay rate of the chemical.
Yeah.
What would you expect if the decay rate is very high? Are you going to have any chemical at the end? No. If the decay rate's high, you're always going to get a low value of A, no matter what your initial value is. Did that work? Did it work for people? Were people able to get that to run?
I am doing a different thing. I'm doing nested for loops, which is probably wrong, but I was trying to loop over multiple values of, you know what I mean, of like K2 and of yeah, but it's kind of hard to see.
Yeah, no, that's what I was originally going to ask people to do, was to try lots of different values of A. And if you really want to do this right, you do have to do that. You have to vary the values of A, the initial values of A. In this case, I happen to know that there are only two. And so I know if you pick a small of A0 to begin with and A40 to begin with, you'll always get both.
Oh, so I wasn't doing it wrong. I was just getting a zigzag like up and down.
Oh, well, that's because of the way you have to organize your lattice when you plot it in plot array.
Oh, okay. Okay.
That's why I did it as all across for high values of A and then across for low values of A. Because if I alternate low value, high value of A, it'll draw the lines back and forth like that. Now, in this case, actually, all the action happens between 0 and 0.2. So let me zoom in on that. Here's K2. Here's A, final value of A. If K2 is 0, well, I know that if K2 is 0, I have no decay. Actually, the total amount goes to infinity. So it doesn't make any sense. So this actually blows up when K2 is 0. When K2 is very small, I get a lot of A star. Regardless, I have two levels, but they're both high. At a threshold of 0.05, I see my lower value of A switches to 0. It saturates at 0. It locks down to 0. My upper value stays positive until a value of K2 of about 0.13, at which point it shuts down as well. And again, this is called a bifurcation. And here are the plots if you do the other ones. And so for each one of these parameters, K1, if K1 is too small, I don't get any product. If K1 is big enough, I get a high value and a low value that depend on my initial value. If B is small, I get a high value and a low value. If B is too big, I only get the high value. If K2 is small, I get a high value and I get actually basically Brunaway result. I get only high value if K2 is very small. If K2 is intermediate, I get a high value and a low value. And if K2 is too big, I only get a low value. So I actually see some sort of interesting things. With B, when B is small, I get two values, and when B is big, I only get a high value. With K1, when K1 is small, I only get a low value. And when K1 is big, I get a high value and a low value. For K2, if K2 is small, I only get a high value. If it's intermediate, I get a high value and a low value. And if it's high, I only get a low value. So I see three different patterns of behavior as I change a parameter. Question, William.
What do you mean when it's intermediate?
Well, so here, if I look at, let me fix this one, because the problem with the K2 scan is I have to be a little bit more careful about what I'm doing, because there's some instabilities there. But let me fix this K2 scan a little bit. I have to run for longer. And I better start with K2. Okay, can you see this on the right? So if K2 is very small, I only get a high value of A, no matter what my initial value is. If K2 is very big, big and small relative to this region, I only get a low value of A. In this range between 0.6 and 0.123, I get two values. So when I'm saying intermediate, I'm saying if K2 is too small, I only get high values. If K2 is too big, I only get low values. If K2 is in this sweet spot in the middle, I get a high and a low value. Okay. Okay. We ran over a little bit of time. I appreciate people's patience with any snafus that we've had. You'll have the slide decks. I would encourage people to play with this, because this kind of basic code that we've done here is something you're going to need to use again and again. So I would definitely recommend building a little library of code that you can use to modify. And because you'll be able to take the same code that you've just written here, and you'll be able to change the circuit and run the same analysis for all those different motifs that we wrote down. All right. Well, thank you, everybody. I appreciate again the patience with all the little glitches we've had today.